This is the first video lecture for Chapter 12, which covers the very important topic of regression analysis. Regression analysis is probably the most advanced topic that we'll cover in this class, and it's the backbone of a discipline in economics and statistics. It combines the two. That discipline is called econometrics. Econometrics is useful not just in economics, but in social science research in general, and certainly in business statistics. So we're going to talk about simple linear regression in this chapter. We'll talk about the simple linear regression model, and I'll introduce you to some of the basic terms and concepts in this first video. We'll talk about the least squares method. The least squares method is the method that we use in order to estimate the parameters of the regression model from sample data. We'll be able to assess how well the model fits the data in a number of different ways, but one way is by looking at the coefficient of determination. So that's an important topic here in this chapter. We also need to concern ourselves with the assumptions under which the model can be applied to the data. If the models are violated, then the technique will be less useful. We will also talk about statistical inference and hypothesis testing regarding the population parameters of the model using the estimated regression model. Simple linear regression involves just two variables. That's why it's called simple. So with a simple linear regression, we have one variable that we call the independent variable. Typically we'll denote that x, unless we have a better symbol to stand in for it. Okay, and one dependent variable, that's the variable that shows up on the left-hand side of the equation. And we'll typically use y to stand in for the dependent variable. Since this one is called dependent and this one is called independent, there's some implication here that x kind of runs in the direction of causing y, but y does not run in the direction of causing x. You should keep that in mind. In other words, x is a sort of a predetermined variable, and the causation runs in just one direction, from x to y. I believe that when you construct a simple linear regression model, or regression models in general, they should be backed up by some good theory or some good idea about that causes you to believe that the direction of causation runs from x to y, but not in the other direction. If there's causality in both directions, then there's going to be issues raised by using regression analysis. There are techniques for dealing with those situations, but they're too advanced to cover in this class. So the relationship between these two variables is going to be approximated by a straight line. That's why we call it linear regression analysis. So it's linear, straight line. Now that sounds fairly inflexible, but actually linear regression analysis is very flexible. That's because this linearity is only in the parameters of the model. It's not in the variables in the model. So while we'll have linear parameters and a linear parameterization of the model, we can measure y and x in any units or make any transformation on them that we desire. In other words, suppose, just as an example, that I'm a labor economist and I'm trying to study wages. I can go out and measure wages, let's say in dollars per week, weekly salary, or an hourly wage. Or if I would like to, I can measure annual salary. I can also take those dollars and I can transform them. It's very common in labor economics to look at the logarithm of wages. There are other transformations that are possible as well, and these transformations can be applied not only to the y variable, but to the x variable too. And so that ability to transform in useful ways the y variable and the x variable actually opens up a whole host of functional forms that can be estimated within the linear regression framework. So it's actually quite flexible. If we have regression analysis that involves two or more independent variables, then we have what's called multiple regression analysis, and that is the topic of Chapter 13, the last topic that we will cover in this course. So the simple linear regression model, it is an equation that describes how a y variable and an x variable are related to each other. But the y variable and the x variable won't be perfectly related to each other. After all, this is statistics and there's always some uncertainty. So the relationship between y and x has a component to it that's predictable and a component to it that is not predictable. And the piece that's not predictable in the relationship between y and x, sort of the stochastic piece, is what we call the error term. So in order to get to perfectly capture the relationship between x and y in a linear model, we need not just the predictable piece of the relationship between x and y, which is denoted by beta naught plus beta 1 times x, but we also need this error term, epsilon, on the end to capture the fact that we won't always be able to perfectly understand what will happen to y when x changes, or what value y will take on. When we know the value of x, there's always going to be some variation in the value of y, even after we've controlled for the variable x. Beta naught and beta 1 are our parameters of the model, and you will notice that they're consistent with linearity in parameters. Beta naught, of course, being the intercept, and beta 1 being the slope. And E, again, is what we call our error term. The properties of this error term are extremely important in regression analysis. Essentially, they have to reflect a random process. There can't be anything predictable in the error term. If there is, then you haven't appropriately specified the regression model. This will also be a key to residual analysis and doing diagnostic testing of the results of a regression analysis. So actually, let me back up to the previous slide again for just a second. You will notice that I was able to express the left-hand and the right-hand side of this equation, the relationship between y, my dependent variable, and my independent variable x, with a perfect equality. And that's because I included the error term. But suppose I want to write this out without the error term. If I drop the error term, I won't be able to write this with an equality. But what I could do is I could take the expectations operator through this regression equation. Okay, so we know that the expected value of y is the average or predicted value of y. So if I want the expected value of y, I can express it with the following equation. Notice that the expected value of beta naught is beta naught because beta naught's a parameter. Also, the expected value of beta 1 times x is equal to beta 1 times x because beta 1 is a parameter and x is known. Okay, so we assume that x is fixed in a repeated sampling sense. So this is the predictable component of the regression analysis. So if I want to just talk about the predictable component of the regression analysis, that's the expected value that y will take on given the value of x. You'll notice that this also implies that the expected value of the error term, of course, is equal to 0. There should be nothing predictable about that error term. So its expected value is equal to 0. So when I take the expectations operator through the regression model, the error term drops out. I'm going to show you some graphs of the regression equation, and we'll talk briefly about interpretation, something that we've seen before when we looked at scatter plots and trend lines. Again, this is linear, so beta naught represents the intercept of the graphs I'm about to show you, and beta 1 represents the slope. Beta 1 can be positive, negative, right, or it could even be equal to 0. Again, EY is the expected value of y for some given value of x. Okay, so we have some given value of x, and we keep observing y every time x takes on this value, and on average is going to take on the value beta naught plus beta 1 times x on average. But there's going to be some distribution around that expected value of y too because of that error term. Okay. So what we have here is a graph of the simple linear regression model, the population model again. And beta naught represents the intercept, and beta 1 again represents the slope right here. So with a positive slope, what we're saying is that there's a positive relationship between the value that x takes on, so an increase in x would tend to lead to an increase in the expected value of y if the slope is positive. If the slope is negative, there's an inverse relationship between x and y, right? And the increase in x would tend to be associated with a drop in the value of our dependent variable y. Of course, it's also possible that there's no relationship between the two variables whatsoever, in which case, clearly, the slope of the regression line will be equal to 0. We'll want to be able to collect sample data to estimate these parameters and test hypotheses about them. It'll be important to test the hypothesis as to whether or not beta naught and beta 1 are equal to 0, positive, or negative. And in this class, we'll focus on hypothesis tests about beta 1, the slope. So we have this population regression model with all these Greek letters in it that we've been talking about, betas and epsilons. But ultimately, what we want to do is we want to estimate that model from sample data. We don't know the values of the betas or the values of the epsilons, but we need to get a sample so we can get some good statistical guesses as to what the value of those parameters are. And that is where we talk about the estimated simple linear regression model, which looks a lot like the regression model, except that instead of having the expected value of y, your textbook uses y hat. Y hat stands for the predictable component of the estimated regression model. And instead of having a beta naught, right, before we had beta naught, the corresponding parameter in the estimated model is b naught. And the population model had a slope parameter of beta 1. We don't know the value of that, but we're going to get our best guess at it by estimating a slope parameter b1. Okay. Now, one thing that's left out of this equation is the error term. I'm going to talk about that at the end of the slide. So this is the estimated regression line, and a graph of it would be the graph of the estimated regression line. Beta naught in any type of a plot would be the y-intercept, of course, and beta 1 would be the slope. Okay, so beta naught being our best guess of the population intercept, beta 1, or b1 rather, b naught being our best guess of beta naught, and b1 being our sample's best guess of the population parameter beta 1, the slope. It's hard to keep the betas and the b's constant when you're talking through these slides, or consistent when you're talking through these slides, I'm finding. Y hat is sort of like in the population expected value of y. It's the predictable piece of the estimated regression line. Okay, and then what's left over after we have the predictable piece is what we call the residual. So our residual is sort of like our sample's best guess for each observation as to what E is equal to the error term in the population model. So the corresponding sample estimate that goes along with the population error term is this residual U. So in order to drop the hat that is over the equation here for an estimated simple linear regression equation, in order to drop that and keep an equality here between the relationship between y and x, we need to make sure we include that residual. That residual, it should be clear to you, is equal to the difference between the value that the y variable actually takes on, right, and what the model predicts the value would be. the difference between the actual value of y and the predictable component from the estimated regression equation. That's going to be equal to the residual, and that residual plays a key role in the technique that we're going to use to get our estimates of beta 1 and beta naught. So let's just look at a schematic before we jump in to talking about some of the details of the estimation process. Conceptually, what we've done so far is we said that out there somewhere, there is this regression model. It describes a relationship that we're interested in learning about between two variables, a dependent variable y and an independent variable x, where the direction of causation runs in one direction from x to y. Now we can measure x and y, and then we can transform them if we need to. So we have actually a fairly flexible functional form, even though this is linear, but we have this relationship between the two that can be adequately captured by a model that's linear in these parameters, beta naught and beta 1. But we don't know the values of beta naught, beta 1. We don't know the value of the error term. We can observe x and y, however, for a sample. So what we do is we go out and we get a collection of sample data. The bigger the sample, of course, the better. But a key component, is also that this sample be appropriately chosen to be a random sample. If you don't have a random sample, or if the direction of causation doesn't run from x to y, but not from y to x, there are things in econometrics that you can do to deal with those problems, but they're quite advanced topics and they go well beyond the scope of this class. So we need to assume that when we collect this sample data, that we have either a simple random sample in a cross-section, or we have random sampling if it's a time series. And more data is better than less data. But if you have a sampling problem, you can have all the data in the world. It's not going to solve your sampling problem. Okay? So we're going to collect this good sample. So assume we have a good random sample, a sample of adequate size. And then we're going to go and we're going to talk about a technique that you can use to go from that sample to the point estimators, B naught and B1. Those are our point estimators of beta naught and beta 1. So these are sample statistics, B naught and B1. And of course, every time we select a different random sample, we're going to get slightly different answers. So we have to treat B naught and B1 as though they're random variables and they have sampling distributions. So if we're going to do hypothesis testing about beta naught and beta 1, or look at the adequacy of our model, we're going to have to concern ourselves with the sampling distributions of B naught and B1. Those are random variables. Beta naught and beta 1 aren't. They're population parameters that we're trying to learn about. We're assuming they're fixed. They're not random variables, but our estimators of them, those are random variables. So all the work that we've done so far on sampling distributions and hypothesis testing, we're going to be able to bring all that work to bear here in understanding both simple regression analysis and multiple regression analysis, two very important and powerful tools in statistics. So let's talk about the method that we actually use in order to estimate our B's, our beta naught and beta, estimate B naught and B1, our sample estimates of beta naught and beta 1. We use what's called the least squares criterion. Okay, that's the criteria that we use, and it's really a problem in calculus. So we're not gonna go through all of the details of the calculus here, but I think that you guys should have an appreciation at least for what goes on here in terms of the optimization problem. So really what we have here is we have each individual observation yi, and what this is beta naught plus beta 1 times xi. That is yi hat. Okay, so really what this is it's the sum of the residuals, each residual I squared. Okay, that's really what this is. This is a much simpler expression of what's here in this equation, but they're exactly the same thing. The residual is equal to yi minus y hat I, and y hat I is obviously equal to the predictable component of the estimated regression equation. And so What we do is we take every single observation and we subtract beta naught plus beta 1 times xi. Now before we do this optimization problem, we know all our yi's and we paired them up with all of our xi's. So we can go ahead and we can do this type of a calculation for every single observation that's in the data set, n times if there are n observations in the data set. But what we don't know is we don't know beta naught and beta 1 yet. We're trying to estimate those. So those become the sort of the focus of our optimization problem. And what we're going to do is we're going to pick them. We're going to pick the values of beta naught and beta 1 so that they minimize the sum of the squared deviations, right, from the regression line. So we're going to minimize the sum of the squared residuals. We're going to make the error as small a component of the estimated regression line as possible so that we're maximizing our predictive power from the regression model in some sense. You can think about it that way. So we're minimizing with respect to beta naught and beta 1. We call those in optimization our choice variables. So our choice variables are beta naught and beta 1. So basically what we do is we take this equation and we take the derivative of it with respect to beta naught. We set that equal to 0. We take the derivative with respect to beta 1. We set that equal to 0. And then together using that set of equations, what we call the first order conditions, we come up with equations for beta 0 and beta 1 that meet or match this least squares criterion that minimize the sum of the squared residuals. So, just in terms of like a graph, if I had x on this axis and I had y on this axis, and I've got some relationship between the two, all these little dots are different data points, right? The line of best fit that goes through here is going to minimize the deviations, the sum of the squared deviations of all of these different points, right, between the regression line and the point itself. The difference between the two is a residual. There's a residual, there's a point here, there's a residual. We want to take all these residuals, square them, add up the result, and have that as small as possible. That's a line that fits through the data that matches the least squares criterion. Okay, so it's pretty intuitive when you think about it. So yi is the observed value again, and y hat I, right? That's also a component of calculating the residual, the estimated value of the dependent variable for the ith observation. So I'm not going to ask you to actually do the calculus, but I am going to show you the equations that are used, that are the result of that process, that are used to get our estimates beta naught and beta 1. Okay, and I'll show you these equations for the simple linear regression model. By the time we get to the multiple regression model, we'll pretty much depend on the computer to do all of these calculations for us. So we'll really be integrating the Excel computer work with the lecture material in that last chapter. We really won't be able to pull them apart anymore. We could still pull them apart a little bit in the simple case though. So this is the equation for beta 1, the slope. What we do is we take each observation xi and its deviation from its mean, each observation of yi and the way it deviates from this mean, and we multiply those two things together. Looks a lot like the equation for covariance. It should remind you of that actually. Okay, it's not exactly the equation for covariance, but this is similar to it. And so we take the product of those deviations, observation by observation, we add them all up, and we divide that by the sum of the squared deviations of xi, the dependent variable from its mean. So the denominator here looks very familiar in terms of the variance of x, right? Except that we're not dividing either of these by any degrees of freedom. But of course, if we did, we would find out that beta 1 really is the covariance between the two variables x and y, right? Divided by the variance of x. So what that means is that to get the slope coefficient, we need variation in x, because you can't divide by 0. So x needs to vary, right? And then the stronger the covariance between x and y, as x varies, the more significant or the more important the relationship between the two, which would be captured in the value of beta 1, the estimated slope coefficient. Once we have the value of B1, it's easy to calculate the intercept. Now, and here's the reason for this. And this is all of this stuff really does apply to multivariate regression as well. You just have to think in more than 2 dimensions. But when I have a regression equation and I've got x on the horizontal axis and somewhere there's some x bar in the data set, the average value of x, and I have y on the vertical axis and somewhere there's some y bar value, the average value of y, that point x bar, y bar is going to be on the regression line. The regression line is going to pass through it. So given that the regression line passes through it, it's easy just to go to the data, calculate y bar, calculate x bar, right? I've already calculated B1 in the previous step, so I can use just the regression equation itself to solve for beta naught. Since I know that the regression equation passes through y bar and x bar, I just plug those 2 points in. I plug in beta 1, I solve for beta naught, and I can estimate the intercept coefficient.